Good morning, everybody. Wow, my hair is looking wild. All right. Let's get the usual things going. Let's see. Grab the. Guess there's so many things on my little notes here. There we go. Here are the usual links to the attendance and the tutoring. Please go fill out the attendance. As usual, I'll post those again in just a moment. So my brain's a little bit tired, and I've been trying. I don't remember which class I said we would be covering on Tuesdays anymore because I just can't remember. I feel like I said FAM, but I honestly don't remember. That said, I do kind of feel like maybe we should give more attention to the Merkx class this week because they have a midterm on Friday. Okay, so I said Merkx, great, awesome. So today's a Merkx day anyway, so I feel fine covering Merkx, even if it wasn't. But good, I was really trying to remember this morning. Gosh, is today Merkx or today FAM? And I was having trouble recalling. So great. So we're going to focus on Merkx today, and he definitely has a midterm on Friday, and he posted I don't want to call it a practice midterm exactly. He posted a study guide with lots of stuff on there, and we can definitely talk about any and all of it. So is there anything? I feel like I was going to ask if there's anything you guys specifically want to cover, but what I really feel like is I think people have asked me most about the shell method lately and volumes in general. So I kind of feel like we should start just doing some volumes. And if you guys have other questions, feel free to ask or write them in the chat. Unless I'm way off base, but I feel like volumes are kind of where people have a lot of questions. So unless there's a strong no from everybody, I'm going to start doing some volumes. Also, again, I apologize for the noise from the construction work going on outside. I don't think you guys can really hear it too terribly. I can hear it. It's really distracting to me, so I will try my best to ignore it, but it is definitely there and making it hard for me to brain appropriately. All right, so let's do some volume. So actually, let's take a look. I'm just looking at his practice or his, so he's got volumes using disk washer. There's something I want to see here real quick. So I'm looking at his so one thing to note. So I just want to see real quick. So under the volumes part on his handout, on his what's this thing called? The midterm 2 review sheet. So on the volumes, I see that there are volumes using the disk and washer method. And then I see that there are volumes using the method of cylindrical shells. But what I do not see, which I'm glad to not see, is the volumes using slices. So I don't see that on here, which should mean that it shouldn't be on your midterm 2, which is good because those are definitely like the worst ones. So that's good. So I will not focus on those unless somehow, somewhere, someone has said that they will be under test. But I don't see them, so that's good. Okay, so let's start with an example. Let's see. Let's start with an easy example, and then we'll do a harder one. So let's find all the words. I should find a light in here. So I want to find the volume of the solid generated by revolving the region bounded by what have I got here? Sure. Y equal to the square root of x, y equals 6 minus x, and y, and the y axis about y. Merkx class is also doing probability, but it's not going to be on their test. Their midterm too, anyway. But that's what it says here. We can definitely do some probability stuff. We can definitely do more probability stuff on Thursday. Although I will probably also devote some time to prepping for the midterm on Thursday because the midterm on Friday. Sure. So I'm just trying to look at one thing on this practice test. There's so much on this here. Okay, sure. So let's set this up. And I think for these problems, you are going to want to draw a picture. I'm imagining, I don't actually know. I don't remember what you're allowed to use during your test. Your midterm is Wednesday. Why did I think it was? Sorry, I thought it was the 22nd for some reason. Maybe I'm thinking of someone else. Oh no, it's definitely the 20th. Yeah, sorry. Okay, so Thursday we won't have to do midterm prep. All right. So for this problem, let's set it up. And if you're allowed to use a graphing tool, use a graphing tool. If you're not, you should graph it. And it's not too terrible to graph. Y equal to the square root of x looks like this. Y equal to 6 minus x is a straight line, has a y-intercept of 6 and x-intercept of 6. And then the y-axis is this here. So be careful, right? That means we're looking at this region right here. And we're going around the y-axis. So you could use either method. I don't know if he's going to tell you which method to use or not. But for this problem, I definitely, regardless of which axis I'm going around, I want to use a vertical strip because a horizontal strip would be terrible here. A horizontal strip would have a different right boundary. Right? So I don't, so a horizontal strip would have, right, this right boundary here, this left boundary here, but down here we have a different right boundary being the square root of x. So we don't want to pick strips that have different boundaries depending on how high or low they are. So instead, I want to pick a vertical strip because a vertical strip, no matter how far left or right it is, the top boundary will always be the function y equals 6 minus x, and the bottom boundary will always be the function y equals the square root of x. So that's the way we want to pick it. And then after you pick what kind of strip you're using, that's when you have determined which method of integration you use. Right now that I'm using a vertical strip and my strip is parallel to my axis of rotation, we have to be using the shell method. Right? Shell rhymes with parallel, so we know it's shell. So here's what we're going to do. We know for our shell method, the volume of a shell is 2 pi r h d. In this case, it's going to be dx because I'm using a vertical strip. Right? We know it's x, but it's vertical. Right? What I'm really thinking of, right, is the width of this strip is just some small change in x, some dx. So our job for the shell method is to identify what the radius is and what the height is. So unlike the washer method, where the radius is how far the top is from the axis and the bottom is from the axis, for the shell method, the radius is how far the strip is from the axis of rotation. So this entire strip being parallel to this axis is how far away from the axis? Well, it's x away, right? Where x is going to be between whatever limits of integration we've got here, which we haven't found yet. So we see that our radius, and actually maybe a better picture here. Sorry, hid my eraser for myself. Right? I'm thinking of this strip. Oh, sorry, that was loud. The strip is located at x, where x is going to go from 0 to whatever this point is right here. So the radius is x. Because I'm thinking of revolving this around the y-axis and getting a cylindrical shell that looks like that, right? Where the radius of this shell is exactly just how far we are from the y-axis. So generally for these problems, these shell problems, the r, the radius, is just x if you're going around the y-axis, or it's just y if you're going around the x-axis. We'll see how to change it if we're going around a different axis in just a second. The height is the height of the strip, which is just the top function minus the bottom function. So here that's going to be 6 minus x minus the square root of x. So we're almost ready to set up our integral. The volume is going to be the integral. I usually put the 2 pi out in front. And then it's going to be x times this, 6 minus x minus, I'm going to write x to the 1/2 instead of the square root of x. Here's the attendance again, in case you guys need it. The only thing left to find is the limits of integration. And this is the kind of problem where you could set these two equal to each other to find this point, and that'd be perfectly fine. But especially when you've got a square root, it's often easier just to guess, because unless someone is a terrible person, they've probably made the limits of integration fairly nice. So it's not going to be some like square root of 3 thing. You're going to say, or 3, I guess. I'm going to try plugging in values of x that are easy to take the square root of. Like I could plug in 0. Well, if x is 0, y is 0. If x is 0, y is 0. Well, that's not it. So then I try 1. If x is 1, y is 1. If x is 1, y is 1. Okay, that doesn't work. And then I try 4. If x is 4, square root of 4 is 2. If x is 4, 6 minus 4 is 2. Oh, 4 is the place where they intersect. That point right there, that's the point 4, 2. You could also do it by setting them equal to each other, right? You could totally do, I'm going to erase it here because I don't really need this. You could totally set the square root of x equal to 6 minus x, and then square both sides, and do the whole solving a quadratic, which is fine. It's not the best, but you're getting x equal to 36 minus 12x plus x squared. And if we bring everything to the right, you get 0 equal to x squared minus 13x plus 36. And that factors is x minus 9 times x minus 4. So you get x equal to 4 or x equal to 9, but 9 isn't actually a solution because it's an extraneous root. So we get x equal to 4. So that's the long way of doing it, but you could totally just guess here, and that would also usually work just fine. So our limits of integration are from 0 to 4. And then the rest is kind of just gross. It's going to be 2 pi times the integral from 0 to 4. And we distribute the x. Make it 6x minus x squared minus x to the, let's see, x to the first times x to the 1/2 is x to the 3/2. And then we're going to integrate. So let's go to the other side of the board. I had a 2 pi integral from 0 to 4 of, what was that again? 6x minus x squared minus x to the 3/2. Okay, so then we have to do the integration. And this is where hopefully you guys are allowed to use a calculator, because I mean, not that it's impossible, but the numbers do get not nice. So 6x squared over 2 is going to be 3x squared, x cubed over 3, and then x to the 5/2 divided by 5/2 is x to the 5/2 divided by 5/2 is multiplied by 2/5. And then we plug in. I can see here that when I plug in 0, everything's going to be 0, so I'm just going to worry about plugging in the 4. So you get 3 times 4 squared, which is 16. I get 4 cubed, which is 64, 3. And I get 2/5 times 4 to the 5/2 is 2 to the 5th, right? Because it's 4 to the 1/2 power is the square root. So that's 2, and 2 to the 5th is 32. And then the rest is just doing a little bit of arithmetic. 3 times 16 is 48, minus 64 thirds, minus 64 fifths. Honestly, I'd probably stop here or even here if this was on a test and it was low on time. If you've got plenty of time, then go ahead and do the rest of this. I would, geez, I don't love this. I guess I need to calm it down here. Multiply by 15. I did right because I don't know what 15 or 15. 48. So multiply by 15 isn't that bad. Multiply by 10 and then you add half of that. 48 times 10 is 480. Half of that is 240. 40 plus 240 is 720. So you get 720 over 15, multiply this by 5 over 5, and you get 320 over 15. Multiply this by 3 over 3, and you get 192 over 15. And then put it all together, you get 2 pi times 720 minus 320 is 400. And the 400 minus 192 is 208 over 15. So the final answer would be 416 pi all over 15. Gross. Again, depending on what you're allowed to use, right, this might not be quite as terrible, right? You can use a calculator, you can just kind of throw it all in there. But you do want to show your work. So let me modify this question just a tiny bit because I want to show you how it changes in two different ways. So let's go back to the picture on the other side. Let's say instead we were going around the axis x equals to -2. So what I really want is to show you how this changes. And it doesn't change, well, I mean, it changes significantly, but it's not a big like conceptual change. Let me erase all this. Sure. And then I'll remind you what we have. So here's the interval we have for around the y-axis. For around the y-axis, which is just x equal to 0, we have this. We have 2 pi, which means the interval from 0 to 4 of x times 6 minus x minus the square root of x. Right, that was our interval where, we're going to use all the colors today. This was our radius, and that was our height. So, if we change the axis of rotation to x equals -2, our radius is no longer just this distance here, because we're not just going on this axis. Our radius is actually now this distance here, which is still x, but now we have to add on this length of 2. So the way I think of it is it's where my screw, or it's really the right minus the left. It's where this is minus where this is. So it's x minus -2, which is x plus 2. So if I was going around the line x equal to -2, my volume would be 2 pi times the interval from 0 to 4. Now the radius isn't x, but it's x minus -2 times the height still. Which isn't a big conceptual change, but numerically this is even worse to calculate, because then it's x plus 2 times all this, and you have to FOIL it all out. Typically, hopefully, when people ask questions like this, they ask you just to set it up. I would like to imagine that's what he's going to do, but I don't actually know. Let me show you one more thing. Let's do, well, not just one more thing, you know. We can also look at rotating around, say, the line, I don't know, x equal to 5. So for x equal to 5, now this distance is my radius. So this is 5, this is at x, and the difference is 5 minus x. Just like the difference here was x minus -2. So here the radius is 5 minus x. And the volume would still be 2 pi times the integral from 0 to 4 of your radius. Now it's 5 minus x instead of x minus -2, or just x, times still 6 minus x minus the square root of x. So there's a radius, there's a radius, there's a radius. This is a height. This is the height. So the height doesn't actually change, no, regarding if you have a different axis of rotation. The radius does change. So are there questions about any of this? Also, here's the attendance one more time. So questions about this shell method example. Yeah, of course. So let me ask you: do you want me to do a shell method on the x-axis, or a washer method, or a dishwasher method on the x-axis? We can do either. But okay, fair enough. So let's actually look at one where it's the same region done both ways around the x-axis, and then I'll also talk about how you can modify it to be around a different axis. Okay, let's see here. I have to think a little bit. Is this pen any good? Let's find out. So volume of this. So let's just describe the region. So the region. This pen is less than great. Yeah, I've got a good idea for a region. Okay. Yeah, pens are fine. Didn't actually end up going to campus and didn't get new pens, so my pens are kind of starting to die. I've still got a few left. So I want the region bounded by. Let's think about this, James. That's not terrible. Sure, that's kind of terrible. Sorry, I have to think about that for just 1 sec. That would be kind of awful. That would be less awful. We can do that. Okay, bounded by y equal to e to the x. Yeah. Okay, I think this will be good. Y equal to e to the x. Let me start drawing. So y equal to e to the x. And then I don't want it to be super awful, because if I do that, we're going on the x-axis. Yeah, let's make it not dumb. Let's do y equal to e to the x, y equal to e, and the x-axis. So sorry, the y-axis, I mean. So x equal to 0. So I'm looking at this. Here's y equal to e. Here's y equal to e to the x. And here's my x-axis, x equal to 0. So I'm looking at this region here. I'm going around the x-axis. And so if I was given this without any directions to which method to do it, I would definitely default to doing it using a vertical strip, unless I was told specifically not to. I'm going to do it both ways, but I'm just telling you, if there isn't a good reason to change your functions to be functions of y, then don't, right? Like I've got y equal to e to the x, and I'd rather not change that to x equal to the natural log of y unless I have to. And I don't have a good reason to here. So I'm gonna default to using the vertical strip, because I've got things as functions of x. If I was given functions of y, I would probably default to using the horizontal strip without any good reason not to. I will just point out, in the previous example, it made a lot of sense to use a vertical strip, right? A horizontal strip makes you have to do 2 different intervals, which we want to avoid if we can. Here, either kind of strip is fine, because a vertical strip, the top function is always this, the bottom function is always this. A horizontal strip, the right function would always be this, the left function would always be this. So either kind of strip is okay here. So since there isn't a compelling reason to change, I don't. So since I have a strip that's perpendicular to my axis of rotation, I know that's going to mean the washer or disk method, which are really the same method. It's just the washer method means you have an inner radius. And here it is the washer method because our region isn't flush with our axis of rotation. So here's what's happening, right? This is my inner radius. This is my outer radius. And the volume of my washer that I get by revolving this around, which I could probably even draw. Yeah, I think I've got enough room here. Let me try and do a little bit of drawing, right? If I actually draw this thing revolved around, right? Whoops. So kind of like that. There's my washer, right? And the volume of my washer is going to be pi times the big radius squared minus pi times the little radius squared times the thickness. And we usually factor out the pi, but I sort of don't. So then the big radius is just y equal to e, right? And I erased it. Oops. Green pen, where'd you go? So this is just going to be e, and this is just going to be e to the x, because the inner radius is the inner function. I mean, I just feel like creating for cheeses. I don't know why. That's really kind of random. I mean, I know we have cheeses in the house, but like, that seems a little weird. You can taste them almost. Anyway, sorry, totally not on topic. So I've got e squared here, and I've got e to the x squared here. And I did factor out the pi. So the integral to find the volume using the washer method is going to be pi to the integral of e squared minus e to the x quantity squared, is e to the x, or it's really e to the 2x, right? Because when you have something to a power, you multiply the powers, or you can say it's e to the x times e to the x, which is e to the x plus x, which is e to the 2x. I do need to find limits of integration. Clearly, or maybe not, I think clearly, the left limit is obviously 0, right? That's as far left as my scripts can go. The right limit, you actually have to figure out what this point is right here. So I can see that y is e, and it's where e to the x equals e to the x equals e, when x is 1, right? E to the 1 equals e. So this point here is the point 1 comma e. So x has to be 1. Usually, the points of intersection are not terrible, right? Hopefully, things have been designed in a way so that things come out kind of nice. All right, so now we just have to do this. This isn't as bad as it looks. Do be careful and don't get fooled. All right, I want you guys to help me out. What is the antiderivative of e to the second? Anybody? Anybody? That's the derivative of e to the second. I want the antiderivative. But you're on the right track, Martha. You definitely recognize that e to the second is a constant. Ah, you're so close. So you're trying to use the power rule, Leslie, which doesn't apply here because we don't have a, I know it looks like the x squared. Yes, Fernandez got it. Right. So it wouldn't be e squared over 2 because it's not like x squared. E is a constant. So this is exactly, you just use the constant rule and say, oh, the antiderivative of a constant is a constant times x. Right? We can pretend this is like 7. And it is actually pretty close to 7. And 7, the antiderivative of 7 is 7 times x. The antiderivative of e squared is e squared times. Be careful because this does come up and it can be tricky to remember, oh yeah, e squared is just a constant. Its antiderivative is just e squared times x. On the other hand, the antiderivative of e to the 2x is e to the 2x divided by 2. Not because of the power rule, but because it's a mini u substitution, right? We know that the derivative of e to the 2x is e to the 2x times 2 because of the chain rule. So the antiderivative of e to the 2x is e to the 2x divided by 2. And I bet, like, in a similar way, the antiderivative of e to the 3x would be e to the 3x divided by 3. So that probably will come up, and I would encourage you to get that straight in your mind. Oh yeah, this is just not too bad. From 0 to 1, here we have to be careful. We plug in 1, and we get e squared times 1 minus e to the second over 2. And then this case, in this words, in this example, we do, I mean, we always need to check plugging in 0. Here, plugging in 0 actually is going to contribute something. So minus, and then plugging in 0, I get e squared times 0, which is 0, minus e to the 0, which is 1 over 2. And then I'm running out of room. I'm going to simplify it over here. Simplifying this, I have pi times e squared minus half of e squared is, let's just get a common denominator. I get 2e squared over 2 minus e squared over 2 minus plus 1/2. And then we could probably write this as one fraction. It's pi times 2e squared minus e squared is e squared plus 1. So that's how I would operate this. Pi times e squared plus 1 over 2. Okay, so let's do it again, but now we're going to use the shell method, which I probably wouldn't generally do. Like, this is definitely probably an example of a problem that's not great for shell method, but it is certainly doable, I think. I'm pretty sure. Let's draw ourselves the same little picture. And now I'm still going around the x-axis. But now I'm going to draw a horizontal strip, because if I'm using the shell method, my strip has to be parallel to my axis of rotation. So then again, I'm thinking of getting, right, like I'm rotating this around. I drew it long. Right, I'm thinking of getting that. My picture is not the best this time. I mean, not that it was great the other time, but I'm thinking of getting a cylindrical shell shape. Like that. And so my job is to figure out what's the volume of my shell. And the volume of my shell is always just 2 pi r h d dy in this case, right? Because my strip is horizontal, and that horizontal thickness is a small change in y. Okay, I'm going to redraw my picture. I feel like I kind of made it uglier than I wanted to. One of those. Okay. So for the shell method, the radius is just how far your strip is from the axis of rotation. Right around there. So there's my radius. It's just the distance from your strip to the axis. It's usually just the variable. So in this case, the radius is just y, because we're imagining this strip at a height of y, where y is going to go from whatever this number is to whatever this number is. And then the height of the strip is just the length of the strip. So it's the right function minus the left function. In this case, well, so here's the wrong thing to write. It's not e to the x minus 0. The reason it's not e to the x minus 0 is because this is y equals e to the x, but this is x equals 0. So it's not y equals e to the x minus x equals 0. I have to rewrite this as x equals natural log of y. It's going to be natural log of y minus 0. That's going to be the height of my strip. Okay. Yeah, that seems good. So the other way to think about it is, right, we know we're integrating with respect to y, so it wouldn't make sense to have a function of x in our integral. So now for the volume, it's going to be a 2 pi, right, putting the 2 pi in front, that's the integral of r times the height. Now, limits of integration. I know the upper limit's going to be e, because the top is just y equal to e. The lower limit's going to be whatever this point is right here. Well, I know y equals e to the x is this function. I know x equals 0 is this line. So if I plug in 0 for x, I get y equals e to the 0, which is 1. That point is 0, 1. So my lower limit should be 0 or what? Oh, excuse me. Sorry. Is my lower limit 0 or 1 there? You just think. Yeah, definitely 1. Right, it's the y value, right? They're what the limits of integration are the y values. Okay, we're integrating y times natural log of y. This is definitely a time where we would use integration by parts. So for integration by parts, this is actually, I feel like this is actually a good question. Like someone could totally ask this, and it kind of, it's a good question in that it hits a lot of different aspects of the class, right? It's a volume, it's also integration by parts. It's a long question, but it's not a bad question. So for the integration by parts, I'm going to let u equal y or the natural log of y. What's always our first choice for a u thing when we're doing integration by parts? Remember the acronym about not being on time? Yeah, u is the natural log of y. And then before anything else, once you know what u is, you know that dv has to be everything else. So if u is the natural log of y, dv is the y times the dy. Okay, then we find du is 1 over y dy, and dv, or sorry, in v, the antiderivative of y is y squared over 2. So then we just throw it all into the formula. So the integral of y natural log of y. And so if it were me, I would probably do the indefinite integral and then go back to the definite integral. So I'm just going to say the integral of y natural log of y dy is equal to u times v, so y squared over 2 times the natural log of y, minus the integral of v du, which is y squared over 2 times 1 over y dy. Now here's the key to this problem. You have to simplify that derivative. You can't try and integrate it, factor by factor. You have to combine and say like, oh, y squared over 2 times 1 over y is just y over 2. So this is y squared over 2 times natural log of y minus, I'm going to bring out the 1/2, and then y squared over y is just the integral of y. And then we can integrate that, no problem. Then you're getting y squared over 2 natural log of y minus 1/2 times the integral of y is another y squared. So there's my antiderivative. Y squared times natural log of y minus y squared over 4. So now, we can do our definite integral and say, okay, this is going to equal, still have the 2 pi. The integral of something is just the antiderivative with the limits of integration plugged in. So it's going to be that antiderivative, y squared over 2 times the natural log of y, minus y squared over 4 from 1 to e. And then we're going to plug them in and see, and hopefully, we're going to get the same thing we got over here, pi times e squared plus 1 over 2. If we don't, it means we made a mistake somewhere. So I get 2 pi times, let's see, plugging in e, I get e squared over 2 times the natural log of e is just 1, so let's not even write that, minus e squared over 4, minus plug in 1. I'm going to get 1 squared over 2, but the natural log of 1 is just 0. So plugging in 1 for this part, I'll get 0, minus 1 squared over 4. And I'm worried about these 4s, except I have a 2 out here in front, so I think it's going to work. So let's see. Let's simplify. Let's get 4 as my denominator. So get 2 pi times 2e squared over 4 minus e squared over 4. Minus a minus is plus 1 over 4. So I've got 2 pi times 2e squared minus e squared is e squared plus 1 all over 4. And then I can cancel a 2 and get pi times e squared plus 1 over 2. So it's the same. It works out. If I had a choice as to, so if I was just given this problem in the original way and told to do whatever I wanted, I definitely would have done the washer method because it was less work. Right? I didn't have to change anything. But if I had to change it, this is how I would do it. Questions about this before I do one other thing with it? Okay. I think I heard a couple people come in. Here's the attendance one more time. Please do fill out the attendance. I think there were a couple people last week that didn't fill out on Thursday, so everyone, please do it. I would appreciate it. So just to show you how we would set this up if we were going on a different axis of rotation. Let's see. So I'm going to erase most of the stuff here. So I really just want to leave this set up. Yeah. Okay, so let me just write down So here is the integral using the washer method around the x-axis, and it was the integral from 0 to 1, I think. Yeah, 1 pi times the big radius squared minus the little radius squared. Right, and that's how we calculated the volume around the x-axis. What if I wanted to go, say, around y equals -2, which we're not going to calculate because it's going to be awful. So here's the difference. Around y equal to -2, my radius, both my outer radius and my inner radius got bigger. It's still the same setup, right? The volume is still going to be pi times my big radius squared minus my little radius squared times dy. But now the big radius got 2 bigger and the little radius got 2 bigger as well. So here's how it looks. It's going to be pi integral still from 0 to 1. But now my big radius, instead of being e, it's e minus 2 squared. And my little radius, instead of being e to the x, it's e to the x minus 2. Yes, I know I could write +2, but I really like to think about finding the difference between the things, right? This radius is just this function minus this function. This little radius is just this function minus this function. Which is definitely a pain to calculate, right? It's going to be e plus 2 squared, and you actually, well, you probably don't have to multiply this one out because it's fine. But this one here, e to the x plus 2 quantity squared, you would have to multiply it out and get e to the 2x plus 4 e to the x plus 4, and it's just a big old mess. So again, I would never imagine you probably have to calculate something like that, but that's how you would set it up. And yeah, I should say, if we were, so the thing to be aware of is you always want to be subtracting the larger thing minus the smaller thing. So if the axis of rotation is below your region, then you want to do your things minus the axis to find the radius. If the axis of rotation is above your region, like let's say I had an axis of rotation that was y equal to 9, then and so the interesting here is that the one that's the bigger radius actually kind of changes, right? Now I can draw this here. Now, if I'm looking at this strip, this is my larger radius, which is 9 minus e to the x. And, come on, sorry, I'm running out of room in this picture here. And here's my smaller radius, which is 9 minus e. So here, the volume this way would be still pi times the integral from 0 to 1. Now my big radius is 9 minus e to the x, and we square that. And then my little radius is 9 minus e. And if I were just asked to set this up, which no one should ask me to calculate this, that would be terrible. If I was just asked to set this up, I would leave it like this. I wouldn't multiply anything out. I would just say, because this also displays that you understand what you're doing. You're saying, oh yeah, my radius is just my axis minus my function. My radius is my axis minus my function. And this one, it was my function minus my axis because the function was the bigger thing. And this one is my axis minus my function because the axis is the bigger thing. Okay, let's look at how that looks on the other side. So, and let's actually use the same. So here, if we were going around y equal to -2, it's not, so the radius does change, right? So right here, it was that the radius of the washer changes. Here, it's the radius of the cylinder changing, right? So now, instead of my radius being y, my radius is y minus 2, which is y plus 2. So around y equal to -2, it would still be the same integral. It's just instead of the radius being y, the radius is now y minus 2, or y plus 2, which is definitely worse. And then if the radius were up here at y equals 9, that one's terrible. Almost round, maybe not quite dash. Wherever there on y equals 9, then my radius, or the radius of the shell, is going to be 9 minus y. Because again, it's always the bigger thing minus the smaller thing. So around y equals 9, we get 2 pi integral from 1 to e of 9 minus y. That's natural integral y. So for all of these things, whether it's disk or disk washer or shell method, when you change the axis of rotation, the only thing that changes is the radius. For the shell method, the radius changes from either being x or y to being the difference between x or y in your axis. And for the washer method or the disk method, the radius changes from being your function to the difference between your function and the axis of rotation. So hopefully that kind of clarifies all the volume stuff with shell and washer method. I know it's kind of a lot. And let me look here. He didn't really give you any practice problems with shell and I feel like this list of things he gave you is just kind of like a big old list with not a lot of like practice. Unless I'm just missing it. No, I don't really think I am. So what I might do is I might try and post a few volume problems for you guys and then make videos of the solutions. I'm gonna write myself a little note here. So I know there's a lot of videos on the docket to be made today, but that's definitely, let me do some volumes with what I should do. So I'll actually maybe what I'll do is, because typing up something actually is moderately time consuming, but the thing I might do instead is just post some videos with the intention that you should try and do it on your own first. So like, I'll be like, here's the problem, pause the video and try and do it on your own. And then after you try to do it on your own, watch how I do the solution. So I would encourage you to do things that way if you want more practice with volumes. So I think, we could talk about volumes all class, but I imagine there are probably other things you guys might want to see stuff about. Probably like improper integrals, I imagine might be something that people would like to hear about. So I think that's where I'm going to go next, unless there is a strong desire for something else. So speak now, or type now, if you have other things you would like to see that are not improper integrals. Okay. I'll remind you that there's kind of two varieties of improper integrals. There's the variety where you have infinity in one of your limits of integration. And then there's the variety where you don't, where you have like regular limits of integration, or you could also have infinity, but that's kind of extra terrible, where you have regular limits of integration and the function is discontinuous either at one of the endpoints or somewhere in between. And if someone has any sense, they'll just give you an endpoint one because the in-between ones they're just a pain. So let's say here is a, let's look at this. Let's look at the integral from, let's do, sure, 5 to 9 of 1 over the square root of x minus 5. This is kind of standard-esque type of question. Clearly, this function is undefined, or clearly the integrand, right, the function you're integrating is undefined. So I know that I have to rewrite this, and I do think it's important that you're clear with how you rewrite it, right? You have to use the proper notation. Okay, this is going to be the limit as take whatever letter you like, B or T or A. I usually use T. I used to use letter B, but the book got me hooked on T, I guess. Sounds like I'm a T drinking addict, but that's not what I am. So limit is T approaches 5, the integral from T to 9 of 1 over the square root of x minus 5 dx. And really, there's one other tiny thing that he would probably like us to do correctly, which is really I should be approaching 5 from which side? I'm approaching 5 from the right, or I'm approaching 5 from the left. The question I'm really asking is, am I bigger than 5, or am I smaller than 5? Well, the thing about would be if we're between 5 and 9, yeah, we're bigger than 5. I know when you're on the bottom, it feels like it's the smaller, but it's actually the bigger, because you're saying 5 is the bottommost value, and so every other value is bigger. So I'm bigger than 5, which means I am approaching 5 to the right. And then we integrate. So I probably want to rewrite this as, in fact, I could have done it there, as the limit as t approaches 5 from the right of the integral from t to 9 of x minus 5 to the negative 1/2 power. And I really, really, really don't think you need to do a u substitution. You could let u equal x minus 5 and du is dx. And then you'd have the integral of, instead of x minus 5 to the negative 1/2 dx, the integral of u to the negative 1/2 du. But I don't think you need to do all that. I think you need to say, well, this is essentially just, right, it's a linear function, and I've got a coefficient of 1. Nothing's going to change. So the limit is t approaches 5 from the right. And the integral of x minus 5 to the negative 1/2, I'm just using the reverse power rule, meaning x minus 5 to the positive 1/2 divided by 1/2 is the same as multiplying by 2. From t to 9. Right? Or we could have done this. We could have said it's u to the 1/2 divided by 1/2, which is 2u to the 1/2, 2 times x minus 5. I don't think you need to do all that. And then we plug in our limits of integration. Before we take the limit, the limit is t approaches 5 to the right of 2 times 9 minus 5 to the 1/2 minus 2 times t minus 5 to the 1/2. And in this case, you can plug in 5. Right? Sometimes you plug in and you get division by 0, so you just say it goes to infinity. But here I can just plug in t equal to 5, and you get, well, this is going to be 2 times 4 to the 1/2 minus 2 times 5. Plug in 5 there, you get 5 minus 5, which is 0 to the 1/2. And 0 to a positive power is just 0. So you get 2 times the square root of 4, which is 2 times 2, which is 4, minus 2 times 0. So I ended up getting 4. So I would say, so it's probably just fine to say it's equal to 4, but you might need to say it converges to 4. Okay, let's do another one. Let's do that. So here is another of this variety where it's undefined somewhere. Let's do the integral from, sure, 1 to 9 of, that would be terrible. No, let's just not make it terrible. Of 3 over x minus 9 to the 4th. And once again, it is important that you rewrite this integral with a limit. At least it's technically incorrect if you don't. I know it's really like, sometimes you just want to integrate and then plug in 9 and be like, oh, I got the division by 0 or whatever, so it's divergent. But most teachers are going to want you to do something like, oh, it's the limit as t approaches 9, right, because it's undefined at 9. And we should switch this. Instead of being 3 over x minus 9 to the 4th, we should write it as 3 times x minus 9 to the negative. And yes, it would be perfectly fine to bring that 3 out in front. I just didn't because I didn't. So now, oh, and one more thing. Are we approaching 9 from the left or from the right? So are we less than 9 or are we bigger? Think about where we live. We live between 1 and 9. So we're definitely less than 9, so we're definitely approaching 9 from the left. Basically, if it's the upper limit you're replacing with the variable, you're approaching from the left. If it's the lower limit you're replacing, you're approaching from the right. Okay, we're going to integrate this. We're going to get the limit. We should write the limit in each step. C approaches 9 from the left. The integral of this is going to be 3 times x minus 9 to the negative 4 plus 1 is negative 3 divided by negative from 1 to 2. This actually simplifies it pretty nicely. Bring 3 and 3 cancel there. So I really just got the limit as t approaches 9 from the left of negative x minus 9 to the negative. Okay, so now we're going to plug in our limits of integration. Yeah. I think I got plenty of options. So I'm going to get the limit as t approaches 9 from the left of negative t minus 9 to the negative third minus the minus is plus 1 minus 9. All right, what happens when I plug in 9 here? What do I get? One of two things. It's either going to be 0 or it's going to be undefined. Which is? Sorry, there's all this black dust all over my table here. It's kind of gross. What do you guys think? 0, undefined? Important. So 0 is one of the possibilities. So the way I've written here, I think makes it harder to tell. If I plug in 0 here, sorry, if I plug in 9 here, I get 0 to the negative third. It might be easier to see. And this is actually, I recommend, whenever I have a negative power, I really, really prefer rewriting. I would rather write this as the limit is equal to 9 to the left of negative 1 over t minus 9 to the positive third. And the same deal here. This is plus 1 over 1 minus 9 to the positive. Because now I think it's more clear that if I plug in 9, 9 minus 9 is 0. 0 to the third is 0, but negative 1 divided by 0 is undefined. Which means that this is divergent. So 0 to a positive power is always 0. 0 to a negative power is undefined because really what you have is division by 0. So just be aware of that. Right? If you're getting a negative power, you're getting 0 to a negative power. You've got something that's undefined. Let me throw one more of these at you. Let's see. I guess we can do that. Sure. Let me think for ones. Sure. Could do that. That's terrible. No, I don't want to do that. Okay. Let's do the integral from. Sorry, I thought I had a good one. 0 to 4 that, sure. 1 over 2x minus So be careful here, right? It's really, really, so hopefully on your exam, there'll be a section that's just like improper integrals, and they'll say these are improper integrals. Because I can see asking this one and not saying it, and then, so here's the wrong way to do this. Say, oh, I know how to integrate this. The integral of 1 over 2x minus 6 is the natural log of the 2x minus 6 in absolute value divided by 2, right? Because the derivative of the natural log of 2x minus 6 is 1 over 2x minus 6 times 2. So if you divide by that 2 to account for the 2. This is wrong, by the way. We'll talk about how this is wrong. 0 to 4. Plug in 4, you get the natural log of 8 minus 6 is 2 over 2. Minus plug in 0, 2 minus 6, sorry, 0 minus 6 times 6 to the value, so positive 6. And this is totally wrong. Even though it looks like it could be totally fine. The reason it's totally wrong is because this function, 1 over 2x minus 6, is undefined somewhere between 0 and 4. Specifically, it's undefined at 3. If you plug in 3, you get division by 0. This function, 1 over 2x minus 6, has a vertical asymptote at 3. And it does this kind of deal. Sure. And so we're looking at this area here, and that area there. And not that it necessarily has to diverge, but we at least have to check and see what's happening, because definitely it looks like that. And usually, not always, but almost always, when you have a vertical asymptote in your interval, it typically means you're going to have divergence. Again, not always. So here's the right way to do this. You have to break it up where it's undefined. We have to write this as the integral from 0 to 3 of 1 over 2x minus 6 dx plus the integral from 3 to 4 of 1 over 2x minus 6 dx. And here's the way we're going to tackle this. This is the way we always tackle this. We're going to do them one at a time. So you do one of them first, and if it converges, then you do the second one. If the first one diverges, you stop, the whole thing is divergent. Great, we're happy. I'm going to pick the one that seems easier, which is the one that has, I don't think any of them is really easier. I just think the one that's here looks slightly easier. So I'm going to write the integral from 0 to 3 of 1 over 2x minus 6 dx is the limit as t approaches 3 from the left, because they're less than 3 here. The integral from 0 to t of 1 over 2x minus 6 dx. So we already know how to integrate 1 over 2x minus 6. It is the natural log of the absolute value of 2x minus 6 from 2. So that's going to be the limit as t approaches 3 from the left. Let's write it as 1/2 the natural log of the absolute value of 2x minus 6 from 0 to t. Then we're going to plug in the limits of integration. So the limit as t approaches 3 from the left of 1/2 natural log of the absolute value of 2 times t minus 6 minus 1/2 the natural log of the absolute value of 0 minus 6. And now here's what happens. When I plug in t equal to 3, I get 6 minus 6, which is 0. And since it's the absolute value, it is a positive, right? Because it's not really 0, it's a little bit smaller than 0. Approaching 3 from the left is like 2.9. Plugging 2.9 times 2 is 5.8 times 6 is negative, but the absolute value is positive. When the natural log, when the argument of the natural log function is getting closer and closer to 0, that means the natural log function is going to negative infinity. Right? This part here is going to negative infinity because, right, if you think of the natural log function, the natural log function looks like this. And as the x values get closer and closer and closer to 0, the y values get more and more negative to negative infinity. So this is going to negative infinity minus, I don't really care what that is, minus 1/2 natural log of 6. So this part, this half, or this portion of the integral diverges. So we're done. The whole thing diverges. And here's what you can't say. You cannot say that it diverges to negative infinity. You can only say it diverges because, I mean, so you could do more work, you shouldn't. You could do more work to see that the other side of the integral also diverges to positive infinity. And since one is diverging to infinity and the other is diverging to negative infinity, we really don't know if it's diverging to infinity or negative infinity. So we just say it's divergent. And that's always the case. Whenever you have more than one piece, if one of them diverges, you just stop and say it diverges. You don't try and say if it's a positive or negative. All right, questions about that? Sure. So let me go to the other side real quick. Okay, so we're looking at this. We are at the limit as t goes to 3 from the left of the natural log of the absolute value of 2t minus 6 minus the natural log of the absolute value of 0 minus 6. That's what we're looking at. And so what's happening here is we're essentially, right, we're plugging in this 3 for t, right? So what I'm thinking about here is I'm getting the natural log of essentially 0, right? It's a number that's really close to 0. It's actually a number that's slightly negative. And so I'm thinking, I got the natural log of 0. And actually it's positive because, right, it's slightly positive because of the absolute value. So what I do is I think about, well, I know what the natural log of is, right? I look at natural log of x, it looks like this. What I'm saying is, so I'm trying to take the natural log of 0. So I'm trying to let the x value be 0. So if I take the limit, right, as x goes to 0, it's kind of funny. Not good $10. There's my limit. So if I'm letting x go to 0, I'm saying, well, I'm coming at 0 like this. And I'm coming at 0 from the right because, again, it's the absolute value. So my insides have to be positive. So if I approach 0 from the right, the natural log function does this thing where it has to go more and more and more negative. So that's how I'm saying that this portion right here is going to negative. And that's always going to be the case when you have the natural log of something that's getting closer and closer to 0. Is that the natural log of something that's getting closer and closer to 0 is going to negative infinity. It's very much how, right, the limit as x goes to 0 from the right of 1 over x cubed is going to positive infinity. Because again, you have something where the argument's getting close to 0 and the whole function is blowing up to infinity. Here, the argument's getting close to 0 and the whole function is blowing up negatively to negative infinity. But really, the way I think of it is just graphically. I'm like, oh, I know that the natural logarithm function gets negatively infinitely large as we get closer and closer to x being 0. That's how I really try to do it. Just like 1 over x cubed, right, that function looks like this. So as x approaches 0 from the right, the y values approach positive infinity. Same kind of idea. It's really just that I know what the graph of this looks like, so I can justify to myself that that's happening. Now on a test, I don't think you need to show this graph. I think you're perfectly valid to just state that if you see that the insides of the logarithm are going to 0, that the whole piece, the logarithm of that thing going to 0, is going to be approaching negative infinity. I'm out of water. It's all right. I can last for 10 minutes without water. Other questions about this? It's a good question, Martha. I feel like I saw. Okay, here's a, I think not too terrible looking integral. Integral from 0 to pi over 3 of sine of x times cosine squared of x. I think something like this would probably be fair game. I definitely see these listed trig integrals on here and talked about using a u substitution. Yeah, I think this seems plausible. So I've got sine of x times cosine squared. It's definitely a u substitution. It's almost definitely a u substitution. You have a sine times a cosine. So the question here is, what should we let u equal? Should we let u equal sine, or should we let u equal cosine? And I can see making an argument for either one, but there's only, here there's only one right answer. So what am I going to try? Should I try sine first, or should I try cosine first? Yeah, it's like, we don't care. Right? Good. Martha, you picked right. It is definitely cosine. But here's why it's not sine. If I was going to pick, so people, I would probably ask a question like this because people really want to pick sine. And the reason, at least a lot of people want to pick sine is because the derivative is positive. But here's the problem. Pick u equal to sine, so don't do this. Pick u equal to sine. The du is going to be the derivative of sine, which is cosine. But the problem with cosine is I don't have just cosine, I have cosine squared. So if I rewrote this as the integral of sine times cosine dx, right? Writing cosine squared is times cosine. Here's my du. Here's my u. Oh, there's a leftover cosine. That's terrible. I can't do anything with that. Instead, we should make the right choice, which is exactly what has been said, which is u equal cosine. So u equal cosine of x. We're slightly disappointed in that our derivative is negative sine of x dx. It's not a big deal. We can always handle a negative. So multiply both sides by -1. So negative du is positive sine of x dx. And I really do like to do one. I would probably rewrite this just to make it extra super duper clear that I've got cosine squared x times sine of x dx. This sine of x dx, that's going to be negative du. This cosine squared is going to be u squared. This is going to be the integral of u squared times negative du, and let's put the negative out front. All right. Personally, I think we should change limits of integration. I'm always a fan of changing limits of integration. Well, I'm mostly a fan of changing limits of integration. Either way here, you're going to have to know how to evaluate cosine or sine of pi over 3 and 0. So what's so I should say, right, for x equal to 0, which is the lower limit, that means u is going to equal cosine of 0. And what's cosine of 0, everybody? Excellent. It is 1. And then for x, so that's going to be my lower, right? Because if it's 0 here, right? If x is 0, u has to equal 1 has to go in the same spot. And then if x is pi over 3, u is going to be cosine of pi over 3, which is what? There's two possible choices in my mind. It's either the square root of 3 over 2 or 1/2. And it is, drum roll please. It's 1/2. Right? If you're thinking about it, cosine of pi over 3, cosine of 0 is 1, cosine of pi over 6 is root 3 over 2, cosine of pi over 4 is root 2 over 2, cosine of pi over 3 is root 1 over 2, which is just 1/2. So the cosine values get smaller in the first quadrant as you go from an angle of 0 to an angle of pi over 2. If you're not sure, you can definitely review your unit circle. Take it 1/2 here. You can totally do it like this, right? You can totally do negative u cubed over 3 from 1/2 to 1. But some people, myself included, would rather rewrite this as, it kind of works out great because you have this negative out here, and when you change the limit order, when you change the order of the limits of integration, it changes the sign. So I can write this in the way that's standard, right? Where the smaller value is on the bottom, the bigger value is on top. And by changing that, I get rid of the negative sign. So it's kind of a win-win. Either way would be fine though. So integrate this, you get u cubed over 3 from 1/2 to 1, which is going to be 1 cubed over 3 minus 1/2 cubed over 3, which is kind of gross. It's 1/3 minus 1/8 over 3. Okay, so that's 1/3 minus 1/8 times 1/3. So 1/3 minus 1/24. Multiply this by 8 over 8 to get 8/24 minus 1/24, which is 7/24. There are probably other ways of doing that, but that's the way I would see it. Let's see what else I had. Let's throw in a quick partial fraction problem. So there is a quiz posted this week. I definitely sent you guys an email saying, especially for the Merkx class and having midterm tomorrow, don't sweat the quiz, right? If you're studying for a midterm, preparing for the midterm, you don't have time to do the quiz, not a big deal. For those of you in FAMS class, I mean, it's, as I said, it's optional for everybody, but if you have the time and the will, please do it. It's good practice. Yeah, that's terrible sounding. There is a use of numeration by parts, and you think a partial fraction problem on there, so you should look at this. Let's look at one partial fraction problem real quick. Let's say, yeah, I care more about the writing of it than doing it. So let's say we've got the integral of, and this is probably going to be not excellent, x squared plus 3x minus, ooh, let's be careful, James, minus 5 over, yeah, x to the 4th minus x to the, ooh, be careful. It's not what I want. I was trying to be tricky. Let's just be smart. X times x minus 1 cubed. Yes. There's my partial, so there's my integral that is clearly written in a way that implies that we should be using partial fractions. Right? If you see an integral written like this, where the denominator is already factored, or factors really obviously, like you got something like where the bottom was x to the 5th minus x to the 3rd, right? That's a pretty obvious, oh, the bottom factors, right? You can pull out an x cubed and then there's still an x squared minus 1, which factors further. Right, so this would be looking like, that's how that denominator would fully factor. If you see that the denominator factors easily, or is already factored, someone is trying to send you a message that is most likely integration by parts. So then we have to do the partial fraction decomposition. So in this case, I have my original thing. And now, let me ask you guys, how many pieces should there be in my partial fraction decomposition? 2, 3, 4, 5, 6, how many? Excellent, you guys are on top of it. So it's going to be a over x, and then it's going to be stuff over x minus 1 cubed and the smaller powers. For me, I always like to write the smaller powers first. So I'm going to write this as b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. It does not matter which order you write them in. I just happen to prefer to do it this way. And then you're going to multiply. So however you get to the next step is fine. Just remember, if you get stuck, what you're doing is you're multiplying everything by that common denominator. So that over here, right, this times this should always just end up being your numerator. Because the denominator, oh yeah, if you got to go, feel free to go. I'm going to finish this problem though. So feel free to take off if you need to go. But for those of you that want to stay, I'm definitely going to finish this problem. So we multiply this times this, and you see the numerator. And then we multiply this times all of these things. What should happen is that you shouldn't have any denominators, right? All the denominators cancel. So this times this, the x's cancel, and you get a times x minus 1 cubed. This times this, the x's don't cancel. One of the x minus 1's cancel. So you get x minus 1 squared. And then here you get 2 of the x minus 1's cancel. So you get c times x, x minus 1. And finally, this times this, x minus 1 cubed completely cancels, and you get d times x. And when you have a repeated linear factor like this, you're always going to eventually have to do something other than just finding nice values of x. We always start with the nice values of x. So I'm going to use x equal to 0. I'm going to use x equal to 0. I'm going to get 0 plus 0 minus 5 on the left equal to a times negative 1 cubed is negative 1 plus b times 0, c times 0, d times 0, all those are 0. So I get a equal to 5. When you're using the convenient values of x to make a lot of things 0, everything should be 0 except for one. Everything on the right should be 0 except for one of the terms. Similarly, I'm going to use x equals to 1. I'm going to get, so we have to plug in 1 for x. So we get 1 plus 3 minus 5, which is 4 minus 5, which is negative 1 on the left. And then I get 0 plus 0 plus 0 plus d times 1. So d is going to equal negative 1. And these values are turning out pretty nice for what I just made up on the fly. All right, so then we've exhausted all the nice effects, right? The values that make everything 0. So then I'm going to pick something. Oh, sorry, I'm going to equate coefficients. So I'm going to look at the coefficient of, I'm looking for the highest power of x, and the highest power of x I see is x cubed, right? There's an x cubed if I multiply this out and this. So for x cubed, I see that there is no x cubed on the left. So 0 x cubed on the left is going to be, here I get an a times x cubed. Here I get a b times x squared is a b times x cubed. I would not get a c times x cubed, right? This would be a cx squared, and this would be a dx. So 0 is a plus b, but a is 5, so b has to equal negative 5. And then I'm going to go down to the next power of x, which is x squared. X squared is going to be a little bit more work. Oh, x squared is going to be a lot more work. And all right, that's all we can really do. I mean, at this point, you could just pick another value of x to roll it down to finding c, but I kind of want to do it this way. So it's kind of terrible games, but it's terrible. So yeah, we got to do it. So x minus 1 cubed, I'm actually going to multiply it out. X minus 1 cubed is x cubed minus 3x squared plus 3x minus 1. And if you don't know how to do that, that's okay. I don't think this would really come up, but it is in this problem. And then x minus 1 squared is x squared minus 2x plus 1. So I'm looking for all the x squareds. On the left, I've got 1. On the right, here's what I've got. I've got a times negative 3x squared. So the coefficient of x squared would be negative 3a. I've got b times bx times negative 2x. So I've got this times this. I've got this times this. That's going to give me a negative 2bx squared. So the coefficient of x squared is negative 2b. And then finally, I've got a cx squared if I multiply this out. Oh, I didn't make this one. And the d doesn't contribute to x squared. So that's how I'm going to find x squared. Or sorry, I'm going to find c. Because I know that a is 5 and b is negative 5. I've got 1 equal to negative 3 times 5 minus 2 times negative 5 plus c is negative 15 plus 10. This is negative 5. So we completed the partial fraction decomposition, and I'm really kind of shocked that the numbers I made up happen to come out with nice integer values, because that doesn't always happen. So here's how our integral would look. A over x plus b over x minus 1, so minus 5 over x minus 1, plus c, which is 6 over x minus 1 squared, plus d, which was negative 1, so minus 1 over x minus 1 cubed. And then finally, I'm going to erase this. The way you would integrate that, here's how I would integrate it. The things that are over x to the first, I leave as is. So I'm going to write this as 5 over x minus 5 over x minus 1. And then the other things that have a different power, I'm going to write as 6 times x minus 1 to the negative 2. minus 1 times x minus 1 to the negative 3. So then I'm going to use the power rule on them. This is going to be 5 natural log of the absolute value of x minus 5 natural log of the absolute value of x minus 1. And then this is going to be 6 times x minus 1 to the negative 1 divided by negative 1. Right, just using the power rule, which would be negative 6 times x minus 1 to the negative 1. And this is going to be minus x minus 1 to the negative 3 plus 1 is negative 2 divided by negative 2. I know it's a bit long, but that's how you would do that problem. All right, that's all I've got for you guys today. For those of you in Merkx's class, good luck on your test tomorrow. I will try and make a few videos I will make it, I will not try, I will make a few videos this afternoon with some more examples of volumes and probably some improper stuff. But if there's anything else you specifically would like to see, send me a message and I will try and make sure it happens. All right, also office hours this afternoon from 2:30 to 3:30. You all are welcome to come. Please feel free. All right, I'll talk to you all later. Good luck on your midterm. Do the quiz if you got time, but don't sweat it if you don't.